of many years of effort and self-doubt. The self-doubt dominated most of the time. But ultimately, what we came up with was that depending on how warm the ground is, which changes with time of day on Mars, you would see more of a particular version of carbon dioxide on Mars that has the atom oxygen 18 into it. And we can get into the details of that later. And what we found is that it changes with time of day, which suddenly explains why the, let's see, 1, 2, 3, 4 different measurements of this, actually 5, there's another one, that have been made over time by various spacecraft and other people on Earth have all disagreed with each other. One possibility was that the technologies just got better, but it turns out that our claim is that no, it depends on what time of day you looked, and you get a different answer at different times of day. And we'll get back to that later on. Okay. Oh, and the cute little logo in the upper right is something we came up with a few years ago. We needed a name for our laboratory, and we came up with SHARP, Spectroscopy at High Resolution for Atmospheric Research at Planets. So it's not SHARP, it's SHARP. Okie dokie. Well, here's what we're going to talk about. This is Mars from the Hubble Space Telescope. I've never had Hubble time, but they make the pictures freely available because they're nice people that way, even though they don't give me the time. And well, I would have to ask, wouldn't I? I haven't actually ever written a Hubble Space Telescope proposal. I should try that. But I like this picture again because it shows you some critical things. Not only does it just show you Mars globally, but you can see from that sort of blue fuzz out at the edges that Mars has an atmosphere. And like Earth's atmosphere, it doesn't stick out very far. It's really right close to the surface compared to the size of the whole planet. You can also see the South Polar ice cap in this picture. And that's something that people have known about for a long time, of course, on Mars, that it has these polar caps, both north and south poles, and they have both permanent and seasonal versions, or rather components. The permanent version is water ice frozen onto the surface of Mars, and the seasonal version is actual atmosphere of Mars, carbon dioxide freezing out partially onto the surface. And that creates a lot of variability in Mars atmosphere from seasonal variability when the air itself is able to freeze on the surface. Now, water has been an important thing in understanding Mars for a long time, and it actually goes back to the 1960s when people observed with, let's see, what was it? I believe it was Mariner 4, no. Well, one of the Mariner spacecraft. Don't hold me to which one. I think Mariner 4 flew by Mars and made measurements that showed carbon dioxide atmosphere. And then some clever folks here on Earth very quickly figured out, wait a second, carbon dioxide atmosphere on Mars actually can't be there because sunlight would have broken down all the carbon dioxide into carbon monoxide and oxygen billions of years earlier, just because it does that in Earth's atmosphere too. But the reason why we're not filled with carbon monoxide poisoning us all the time is that the water in the Earth's atmosphere also breaks down under sunlight, and it reacts with the carbon dioxide or carbon monoxide in what's called a recycling reaction and gives you it recycles the carbon monoxide back into carbon dioxide. So one of the things that people figured out early on is there had to be some water on Mars. Of course, in the 60s, that was a little risky because all we had before that was claims from Percival Lowell, and before that from Schiaparelli claiming, well, canals on Mars. That's water everywhere. It's civilization. Well, we could see pretty early that that wasn't true. And for a long time, in addition to what Yuck Young and his advisor, I know Yuck better than his advisor, who's McElroy, that's it. They had figured out water. Okay, we had the water, but to actually see it on Mars, well, we didn't have much. Early on, well, we had things like this from Mariner 9, which flew by Mars, or actually it went into orbit around Mars later in the early 70s. I've forgotten which year. This is Nergal Vallis, which is a Persian name or actually a Babylonian name for the god of war, otherwise known as Mars to the Romans. And for a long time, this was the kind of thing we had to say, well, look at that. There may have been rivers on the surface of Mars sometime. So even if they're not there now, there once were. But we had only kind of crude, low resolution pictures like this. And then time progressed. And nowadays we get things like this. Now, this is not actually a picture taken from an angle. It was projected to an angle. But you can now see with pictures that we can get from orbit around Mars, this would have been given who's responsible for it. The Mars Reconnaissance Orbiter has a camera called HiRISE that gets extremely high spatial resolution measurements. And Casey Vallis here, just one of many, but it gives you this beautiful example of a water flow channel. And there's really no question anymore. You see something like this, you can see this looks like things that are on Earth and an area that's called the Channeled Scablands out in Montana. Okay, this is a place where on Earth in the Channeled Scablands about 20,000 years ago, an enormous glacial dam, ice that was holding back a lake of meltwater, broke and allowed a gigantic amount of water. And I will hand-wavingly suggest around the amount of Lake Erie to empty this lake in a day or two, and scraped away a huge amount of terrain, animals, plant life, everything. Well, okay, we don't see the animals, the plant life, the everything on Mars. We certainly don't see glaciers today, but we can see this outflow channel that looks like the kind of thing that we know what happened on Earth. Although, in fairness, it took decades of observations before people were convinced that that was what had happened on Earth too. So for a long time, this kind of thing was the evidence we had that at one time on Mars, you could have liquid water flowing. This happened to be a catastrophic flood. This was not like what we see our normal river valley on Earth. This was a catastrophic event, but still, at one time, enough water piled up that something like this could happen. And that suggests that there was once a reasonable amount of atmosphere on Mars. The amount of atmosphere on Mars today, if you put a puddle of water out, it would just boil away and freeze and sublimate away very rapidly. It just couldn't last long enough to build up billions of gallons of water. Another example, this is actually a different view of Casey Vallis, or Casey Vallis. I'm not sure how to pronounce it. But this is from Google Mars. And in case you didn't know, yes, Google Earth has adapted the same software to do Google Mars. And you can just look it up and have endless fun flying around over the surface of Mars, looking at topographic maps or looking at just, visible light maps, temperature, all kinds of stuff, oodles of fun. But this is another view of that same set of outflow valleys, showing you the structure and showing you that some things, like some of the craters, were there before this valley had its outflow. Other things may have shown up afterwards, like the crater that's over there on the right in the blue area seems to be after that flow, whereas the crater that actually shows flow channels going around it must have existed before the water flowed through. Now I'm going to show you another example of a crater that has water flow associated with it. This is called Gale Crater. This is another topographic map. It's not really these colors, but you can see at the lower left where a river channel broke through the wall and flowed into this crater and created a flow channel on the floor, complete with a little delta of material that flowed out and sedimented on the bottom of it. This is the crater where the Curiosity rover is on Mars right now. And that yellow oval up there shows where the estimated landing ellipse was going to be before the mission. This is pre-mission stuff. The actual landing ellipse, meaning the space in which they thought the rover would actually land, was much smaller in reality because they became really good at targeting these things. by the time they landed Curiosity, otherwise known as the Mars Science Laboratory. The reason they picked this crater out of all other possible places on Mars, and Quesae Vallis was one of the possible places, and Jezero, which we're going to look at in a moment, was another. They picked this because of that weird mountain in the middle. You can see, you may know that craters tend to have a central peak, and you can actually see a central peak. Oh, I'm pointing with my finger. Let's see if I can point with my cursor. There's a central peak right there in this crater. But then there's all this stuff up around it. And what appears to have happened is that that crater filled in with sediment billions of years ago. And then as Mars dried out, the wind carved out the interior of the crater again. And so it excavated what had been put in there, we think, by water flowing in. And in fact, you can see in the side there, it's dug back down to that water flow channel. And certainly when Curiosity first got there, they very quickly found evidence in the floor of the crater from the kinds of pebbles that were distributed and the way they were distributed, that this was a place that water had flowed into at some time. But evidently before all of that sediment got scoured out again by the wind. And so right now what they're doing is they are driving up that mountain, which has been named Mount Sharp. And so because that mountain was formed by sediments that were deposited in the crater and then scoured away by wind again, as they drive up the mountain, they're actually driving through time. So it started at the oldest sediment at the bottom. And as it drives up the mountain, it's getting to the youngest stuff. So the most recently deposited on Mars. And as it passes by, it sees things like this, little outcrops of rock. And if you're a skilled geologist, and I am not, I'm an atmospheres guy, but a skilled geologist evidently can look at patterns in the ridging in these kinds of outcrops and see that, this was rock that was actually eroded by a water flow going by. And in fact, the bottom part of that panel down there, that is the Hummocky Plains unit is HPU, and SU, I believe, is a smooth unit. I forget. But from the way it forms these little shelves, they can deduce that water flowed through here. There were both sediments deposited by water, and then water flowed through and ground it away, giving evidence that there were giant floods in Gale Crater, where the Curiosity rover is now. Other evidence that there was once water there is plain old mud. It's not mud now, but this slab of rock is something that the Curiosity rover came across that appears to have been, this happens on Earth too. If you make in fact, this is an experiment that you could just do if you wanted. Get some dirt, mix it with water, put it outside in a thin layer, and that mud will dry out and it will form cracks. And those cracks tend to form little polygons. Sometimes you'll find, and it just depends on local circumstances. I've seen pictures where they make lovely hexagonal cracks all over with lots and lots of hexagons next to each other. In this case, it made more rectangular cracks. And then sometime after that, water with stuff dissolved in it flowed through and filled in those cracks, which is why you see that white stuff in between. That's actually material that will dissolve in water, otherwise known as salts. The salts were deposited in there as the water dried up again, filling it in and gluing in those cracks in the rock. You also see surrounding this slab, you see black sand surrounding it. On Earth, that kind of black sand is pretty rare in most places, but you can find it in places like Iceland and Hawaii. And what unites them is that they are both cases where you get basalt lava, lava from volcanoes that have actually flowed up from the upper mantle in the Earth, which gives you a relatively iron-rich type of rock, basalt, which has flowed out on the surface and then ground away by, in this case, billions of years. On Earth, a much shorter period of time. by ordinary weathering, by freeze-thaw cycles and wind-blowing stuff, grinding it away, or when it flows out into the ocean, ground away by the ocean, giving you black sand. And we see this kind of thing on Earth. Okay, the rover that has just recently arrived on Mars and the helicopter that arrived with it is in Jezero crater. This is that little crater there is not Jezero. Jezero is the much bigger region that little crater is inside. But you can see over on the left there, you can see a meandering river, actually named for the River Meander in Turkey, or at the time it was ancient Anatolia, and it's a Greek name because there were a bunch of Greek colonies formed in that region about 2,500, 2,800 years ago. So the River meandered, giving us the verb and the descriptive noun way back when. And it happens when a river slows down. When a river slows down, it tends to form these kinds of big bends. And in fact, if it had kept forming a bend like that, you see up in the upper left there, eventually it would have actually silted in and formed a lake. And you get what are called oxbow lakes that are very characteristic of this kind of slow river. But being a slow river means at one time, rivers could take their time flowing on Mars and just flow along. Over to the right, well, actually in the middle of this, to the right of that meandering river, you can see where it flowed into what at one time was a body of water. It spread out a delta of material that built up over time. It left a channel in the middle, and this kind of thing is seen when people do sonar on places like the Mississippi River outflow channel into the Gulf of Mexico. I've seen pictures. Again, it's not my stuff, but I've seen pictures. That crater in the middle, that little one, you can see landed in that outflow channel after it formed. So it comes from some time after that flow of water and is a relatively small crater that's splocked into that. No central peak, which is how I can tell it's a relatively small crater, even though there's nothing else to give us size. And in this picture, which pulls out a little bit farther, you can see that was the landing site that they were planning for the Perseverance rover. And again, well, actually, that one gives you size. So this is the actual landing ellipse. You can see they're getting a little more frisky with their landing because there's a cliff-looking sort of thing in the middle there. And the reason they chose this is because you can see this outflow channel. Also, we've become better at landing these things, and we've become better at having rovers drive, so they can drive faster. And the idea is that the Perseverance lander is going to drive up towards that river flow and take rock samples along the way. It'll drill in and get core samples of those rocks, pack them all together into packages. And as far as I can tell, they went with the plan where it's just going to poop them out and leave a trail of packages behind. I'm a little unclear. This is something that's never been entirely clearly represented in public. Will it just leave a trail of breadcrumbs, which is a more appetizing description, or is it going to drive back to a central location and drop them? I think they're going to do a bit of both. And of course, right now, we're flying that little helicopter around to prepare for the future when maybe more capable helicopters will be something that we can try out on Mars. Now, I've mentioned a comparison object before, and I want to look at that big comparison object, us, Earth itself, seen from the moon in this case. A lot of the stuff that we're looking at on Mars, well, we know it happened on Earth, which is how we're able to understand it on Mars. But, we're not the only two objects in the solar system that have atmospheres and may have once had water. Venus, too. Let's look at Venus and see how these three things compare to get an understanding of what we should be expecting on Mars. And so I'm going to give you a nice little bar graph of what's in the atmosphere of each of these planets. So you can see Earth in the middle right now, one bar, because one atmosphere is a hard to write term when you're talking about multiple atmospheres. So one bar is the air pressure at standard temperature and pressure on Earth. Earth's atmosphere, let me just see. Whoop. That should be able to be readable, but that blue stuff on the left is nitrogen, and next to it is oxygen. And then there's a bit of water and argon and carbon dioxide in Earth's atmosphere. And so you can see on Earth, I've got it in order of decreasing abundance. So there's more water than there is argon, and there's more argon than there is CO2. And you may at that point be wondering, wait, argon? Where is argon coming from? The argon is coming from radioactive decay of rocks in the Earth. And because it comes from that kind of radioactive decay, it's one of the ways people use to figure out how old a rock is. When did it come out of being melted rock, when the argon would have easily boiled out of it, solidified, and then as it continued to undergo radioactive decay of small amounts of stuff, it traps argon in the rock. And so you can use different argon isotopes, that is argon atoms that have different amounts of neutrons in them, to figure out how old that rock is. Now let's compare to Venus and Mars. When you look at Venus, you can say, whoa, Venus has a whole lot of carbon dioxide, and a little bit of nitrogen. And you look at Mars, you say, well, Mars has a whole lot of carbon dioxide, some argon, and a little bit of nitrogen. But then look at the numbers that are underneath them, and you say, wow, wait a second, Venus has 92 times the air pressure of Earth, and Mars has 0.6% of the air pressure on Earth. So even though there's a lot of CO2 in the atmosphere of Mars, you say, well, but there's just not much atmosphere total. But let's look at it a different way. Let's look at how much total stuff there is. And that starts to tell you some things that are hard to understand, because now you can look at Mars, you say, well, Mars has very little nitrogen, very little argon. But if you look at the total amount of carbon dioxide on Mars, it's 8 times the amount of carbon dioxide that's in Earth's atmosphere. It's actually easier to see CO2 on Mars than it is on Earth. And then Venus, what the heck? Venus has almost 3 times as much nitrogen as Earth has. So what's going on there? And it has 157,000 times as much carbon dioxide as Earth does. What the heck? So that understanding that kind of thing is part of the stuff that we're trying to figure out. And in particular, it's like, well, so if Venus and Earth and Mars were born out of the same stuff going around the sun, we would more or less expect them to start off more or less the same. So maybe the question we should be asking isn't how come everything else is different from Earth, but how come it's different from Venus? Because Venus looks like it may have held on to all its nitrogen. So did Earth lose some? Or was it born with less? Or is it someplace else on Earth instead of being in the air? And then carbon dioxide, well, that too. Well, so let's understand a little bit about Earth's atmosphere, because we have better samples than we do for Mars and Venus, and then maybe we can understand this better. So these are some rocks that were given to me by a friend from up by Lake Superior, and they are examples of something that's found all over the Earth called banded iron. Banded iron formations date back to about 3 billion years ago on Earth and up to as recently as about 1.5 billion years ago. So they spent billions of years forming these things, and in particular, they formed in the ocean at the time. And this is a thing that tells us something about ancient Earth. All we have are these rocks, but it's telling us about the air. Because you see, there's a simple experiment that you can do yourself. It's not hard. Just get something like iron filings. You can buy them actually at toy stores. You can buy them at hardware stores. You can just add, craft stores. So years ago, I bought some iron filings and I dumped it into a little aluminum foil cupcake tin. And I put that in an aluminum foil baking pan and I filled it up with distilled water. And I made a couple of versions of this. And in one of those versions, I dropped in a big chunk of dry ice. And then I covered them all with saran wrap. And I let them sit for a week or two. And when I came back after a couple of weeks and looked at it, the water in all of them was nice and clear. But in the ones that I did not put the carbon dioxide in, I did not put the dry ice in, the iron filings were all rusty. Whereas in the one that I did put the big chunk of dry ice in, the iron filings were just a little bit rusty. And then I took off the saran wrap, and over the next hour or two, it formed orange crud all over the inside of my pan. And the reason is iron will dissolve in water, but so does oxygen. And if dissolved iron encounters dissolved oxygen, it immediately forms rust and plops out on the bottom. Whereas if there's no oxygen, the iron can dissolve into the water and spread all over. And for example, it could spread all over the earth if it were dissolving into an ocean that has no oxygen dissolved in it. And then if something, and by something I mean early bacteria, early cyanobacteria, makes oxygen, when it reaches the little cyanobacteria that are making oxygen and pooping it out into the water, it rusts there and settles out of the water. What these deposits are showing us is over billions of years, Earth's atmosphere did not have oxygen in it. So the iron was able to spread all over the world, but there was something making oxygen, and that's when it would oxidize, turn into rust, settle to the bottom of the ocean, and over time form these banded iron sediments that are a mix of different amounts of iron and different amounts of sand. And about 1.5 billion years ago, this turned off. It stopped happening. And instead, what happened was that we started getting iron rusting out on the land because the air now had so much oxygen that when iron deposits that were on the continents were ground away by rainwater and things like that, and it dissolved in the rainwater, now there was enough oxygen that it would just rust out where it was, and you get what are called red beds. So we have a lot of reason to think that Earth used to be more like Venus and Mars, with a carbon dioxide rich atmosphere. We know why it changed on Earth because life developed here. But what else happened? Like, why don't we have as much carbon dioxide anymore? It didn't all turn into oxygen. Well, what it turned into was rocks. All over the Earth, we have these carbonate rocks that are formed when carbon dioxide dissolves into the water. And when there are metals dissolved into the water, like calcium, it can react with the calcium, form calcium carbonate, settle out, and form limestone all over the Earth. Now, these days, more recent carbonate rocks, and by recent, I mean the last, say, 500 million years, are mostly from seashells, because seashells make their shell out of carbonate minerals, out of calcium carbonate. But this is where all the hydrogen and oxygen on the Earth is. It's in the ocean, and most of the carbon is in the rocks on the Earth. And that's part of why we don't have a carbon dioxide rich atmosphere today, although, of course, people are busy trying to change that. Not such a good idea. Do we have any evidence that something like this ever happened? Well, we can't see it on Venus because we haven't been able to send any geology missions to the surface. The missions that have landed on Venus only operated, the record was for 2 hours long, and what they saw looked like basalt sitting on the surface. But we've been able to do a lot of that on Mars, and indeed on Mars, we've seen things kind of like that. You can see sedimentary deposits. This is from the Opportunity rover. So this landed on Mars in 2003. I forget. It's shameful. I should have looked it up. Anyway, they landed, Opportunity in particular landed in a crater, which was awesome because it means it could start looking at things where Mars had been excavated and see right away sediments that had formed in the ancient past. And they saw sediments like these. That ripply structure tells you it formed under liquid water, not mud, so not something like dirt with water in it, but actual liquid water where it could form waves and things like that. Those little round doodads you see all over the place are nicknamed blueberries, and they seem to be actually little iron deposits forming a mineral of iron called hematite that precipitated out. Now, I have never heard from anybody whether anything like that has been seen on Earth, but it seems to be pretty common on Mars, or at least in this area of Mars. There were these little blueberries all over the place. But part of the reason why this place was chosen for opportunity, a similar place chosen for spirit on the other side of Mars, was because spacecraft orbiting the planet had seen spectra that suggested there's some hematite there. And the only way hematite forms on Earth is if iron dissolves into, you guessed it, acidic water, where it's acidic because carbon dioxide is dissolved in the water. And so they thought that's a place that we should go to see if we can find water. Now, all this shows us there used to be a lot of water on Mars, but we can, or rather a lot of air on Mars, because the water was able to last on the surface without all just boiling away instantly. But how much atmosphere was there? A lot of people say, Mars has lost 95 to 99% of its atmosphere. And that makes it sound like you can make a solid estimate for how much there once was. Well, let's see, 95 times, if it's lost 95%, then that means that there used to be 20 times as much atmosphere on Mars as there is today. But if it lost 99%, that means that there was once 100 times as much atmosphere on Mars as there is today. Well, that's a factor of 5 difference. That's a big uncertainty. So that's what we were trying to get at when we made these measurements, when we were trying to figure out the isotope ratios in the atmosphere of Mars. And the reason is that over time, atmospheres tend to get enriched in their heavy isotopes because the light isotopes of things that are gases can escape to space. They just leave. They've gone out to space. They've had billions of years to escape the solar system, leaving more of the heavy isotope behind. And to show how that happens, I have a comedic demonstration. I am going to show you a physics experiment that I unintentionally performed in 1983. It involved a blue Honda Accord hatchback and me on a bicycle. Now, I don't actually have pictures from the time of the event, so I am attempting to reconstruct the events using pictures from other times. That is not the Honda Accord hatchback that was involved. That is not the bicycle that was involved, nor was I riding my bicycle on the summit of Mauna Kea, which is what I was doing when I took this when a friend took this picture in 1993, years after the actual event. So in St. Louis, Missouri, on Big Bend Boulevard, yes, it was on Big Bend. I just had to make sure I had it straight. A car and a bicyclist were approaching each other at high speed. The bicyclist, me, wanted to go through the intersection and legally had right of way. The car wanted to make a left at the intersection, did not legally have right of way, but did not notice the bicyclist who was cranking along at 40 miles per hour. And so there was a kaboom, causing the bicyclist to depart from his bicycle, that would be me, and go sailing across the road. And because momentum and energy were conserved and the car did not slow down very much, the bicyclist, me, started moving much faster than I had been going before, bouncing across the road. If you ever need a particle physics experiment demonstration, it works for that too, because the bicycle and the bicyclist were broken up into 2 separate particles, and the bicycle itself was broken into 3 separate particles. Well, I did survive. All my parts were attached, but I got what are known technically in the field as owies all over my body from bouncing across the road. But the critical point was that part about the speed. I was moving faster because I was light compared to the car. So when the car transferred some of its momentum to me, that caused me to move much faster because I had less mass than the car. This happens with atmospheres too, something that's called Jeans escape. In this case, I'm showing you a little atom and a big atom. And when they bonk into each other, the little atom goes sailing off much faster and is prone, if it happens to be near the top of the atmosphere to start with, it is prone to go sailing off into space, completely leaving the planet. Now, in the real problem we have to deal with, the difference in the size of the atoms is not as big. We actually have two atoms that tend to be closer to each other in size. And so the difference in speed is not as great, but there is still a difference. And so you still tend to lose the little ones faster than the big ones. Now, way back when, and I just forgot to show you a slide of it, the Viking lander on Mars in 1976 to 1979 tried to make a measurement to learn about this. It tried to measure the heavy isotope to light isotope ratio in carbon dioxide, which means oxygen 18 compared to oxygen 16, which is the normal kind, in carbon dioxide on Mars. There's only a little bit of the oxygen 18 stuff. It's only about less than 2%. It's 0.2%, in fact, of the total amount of regular oxygen 16. And they thought they would be able to measure it. And because it was clear that Mars had lost a lot of atmosphere, they should get a big difference in those two. And the thing is, they did not. They got almost exactly the same as we have on Earth, which is hard to understand. So it looked like the atmosphere of Mars had not changed that much in carbon dioxide, and yet they had big error bars on it. And when they measured nitrogen, they found that Mars was enriched in nitrogen 15 compared to nitrogen 14. When they looked at hydrogen, they found that deuterium, that's the version of hydrogen with an extra neutron, was heavily enriched compared to regular hydrogen. So everything was consistent with losing a lot of atmosphere, except for the carbon dioxide, which is most of the atmosphere. So back in 2008, another mission called Phoenix landed on Mars near the poles. It had a camera on a mast that took this spacey looking picture looking down at itself. And they measured the oxygen 18 to oxygen 16. And Curiosity made the measurement too. These plus Viking are the only mass spectrometers, they're called, that have ever landed on Mars. Now, I don't want to go into a lot of detail here, but what they found was it wasn't that different from Earth. It was enriched. But what they found also was that the amount seemed to vary. And if you had more, too much detail. I'm just going to jump past that. Now, where I come into this was that a bunch of years ago, I was asked to make a measurement that our spectrometer is really good at, looking at something funky in the upper atmosphere of Mars, where suddenly it gets really hot at about 70 kilometers above the surface of the planet. It's not actually heat. It's something else going on, but our instrument is really good at measuring this. And so we trucked out to the NASA Infrared Telescope facility, or rather we went by airplane, and we trundled along our instrument to the IRTF to bolt it on the back of this telescope. That part is our instrument, and that part is the electronics set to support the instrument. Now, of course, going from Maryland out to Hawaii is a big trip. So, you got to ship a lot of stuff. Here's an example. Let's do some astronomy. And so astronomy is exactly what we did. We get our instrument out of the case that we have to ship it to Hawaii in. You got to be real careful when it's a one-of-a-kind instrument. We set it up in the interestingly named setup room to the side of the observatory. And we get everything working over the course of a few days. The electronics in the background behind me, some of that we leave out there because we have a copy of it back at Goddard. Other stuff goes back and forth each time. It usually costs us about $6,000 each way to ship all our equipment. So we are really trying to make the instrument smaller, so it won't be that much trouble. So we work on it for a few days. This is just the instrument from various angles with some of the work being done. And then when we have everything functioning, we trundle it back out into the observatory and load it up on the platform below the telescope. And then we crank it up to bolt it to the back of the telescope. Another horrible night of work, because typically we'll get started getting it onto the telescope by about 11 a.m. on the day we need to observe, work on it all day, and then the sun sets and we have to actually observe things with it that night. typically staying there until 6 o'clock the next morning. It is exhausting, but the sunsets are pretty. That, by the way, is the Keck Observatory next door. I have asked them for telescope time, but they have not given it to me. So I like to take pictures, particularly when it's a cloudy day, and their telescope is no better than ours. Ha ha ha. You can also see the moon just a little bit up there in that picture. Our observing station looks like this, and this is actually a picture from one of the times that we were observing Mars 5 years ago, as it happens. We use a really antique computer to run our observing station because it works. And when the night is over, a bunch of exhausted astronomers go out and try to look dramatic, but we can't seem to coordinate who needs to look in what direction for when the picture gets taken. An example of what we look at, and I'm going to try not to show too many of these, is what my colleagues in education and public outreach refer to as a squiggly line plot. I don't want to go into the horrible details here, but the big thing is that dip over on the right side, on the left side of the picture is due to the amount of carbon dioxide that has oxygen 18 in it in the atmosphere. And what we realized was, hey, what the heck is that thing? Well, we figured out what it was because we didn't expect to see it there at all. And then, hey, it doesn't match the model we make when we use an assumed atmosphere. We can use it to measure how much of that stuff. We had a bunch of measurements, so we could make a bunch of different measurements of it. We put them all together to get this little plot again. We could figure out things like temperature of the atmosphere and stuff like that. And we said, okay, let's see what we've got. And what we found is that we suck. All of those little crosshair things with little glowy squares behind them or diamonds behind them are our measurements, and they're all over the place. And when we compare it to the Viking measurement, which is that broad orange bar, our error bars look even worse than theirs. Now in there's another measurement from somebody on Earth, Vladimir Krasnopolsky. He made a measurement kind of like ours, and he got a slightly different answer. And then there's those two blue bars. Those represent the measurements that were made by Phoenix with the lower blue bar and by Curiosity with the upper blue bar. And oh, look, they actually got some enrichment of oxygen 18, and they have great error bars. We are useless. Why do we even exist? But when we looked at our data, we began to figure out, one of the interesting things about Mars is that the temperature changes with time of day. And these are measurements that we made from our own measurements. The scatter in them is because we're looking at different places on Mars and actually watching how the temperature changes on that place compared to a different place. We said, the temperature is actually different in our higher measurements than in our lower measurements. Why don't we try something really clever? Because see, there's the time of our lower measurements. Why don't we try something really clever, and we will compare our measurements to the temperature of the ground at the time we made the measurement. And oh, holy heck, they actually agree with each other in some way. Why is that? Well, we came up with an idea suggesting that when it gets cold at night, the heavy isotope version of carbon dioxide sticks to the ground. And over the day, as it warms up, it comes out. Did anybody ever see that before? Well, we don't know. Viking, it turns out that we actually can't find the Viking measurements that were made over 3 years where they had the chance to make lots of measurements like this. We would actually be able to examine the Viking measurements. Maybe their error bars were much better than they thought, and they made them look big because they saw that the amount they measured was varying, but it didn't occur to them that it might be varying because of this. We looked at the Phoenix and Curiosity measurements. We see them going up and down with both carbon-13 enrichment and oxygen-18 enrichment going up and down together. Maybe they did see this, but they didn't realize that's what they were seeing. Now, I should be clear. I talked to the primary guy who did the work on Phoenix and who was part of the team on Curiosity, and his thinking is that they have failed to understand their instrument correctly. But I have seen too many times now where somebody out of modesty denied themselves a discovery. I don't believe, I think they knew exactly how to do it, They just don't believe it anymore because they don't believe they could be that lucky. So there's our measurements again. And one more thing that we think is evidence that I may be right about this. We have also made measurements. This is from 5 years ago, looking at the northern hemisphere when it was northern hemisphere summer, and looking at Gale crater latitude, which is right close to the equator, at the same time, and then looking at the southern hemisphere at the same time when it was southern hemisphere winter. And if you look at that little dip in the graph, and I'll just point my little cursor at it, right there, that little dip is how much of that oxygen 18 CO2 is in the atmosphere. And whoa, we see it there. It's in the atmosphere in the southern hemisphere. It's in the atmosphere here at the equator, but bingo, it's not there in the winter hemisphere. And so that kind of agrees with what I'm saying. It doesn't 100% agree yet. We have to do some more work on that. And lastly, I'm just going to show you a little bit more on Venus because, I mentioned Venus before. Well, what about Venus? And the answer is we don't know, because we made similar measurements on Venus about 11 years ago. And what we saw real quickly was that where that little dip should be over here on the left, and here, and here, and here, and here, and here, it isn't there. So we need to do a lot more to figure out why it isn't there. Is it not there because there's hardly any oxygen 18 CO2 in the atmosphere? Or is it not there because we don't understand the way the temperature varies in the atmosphere, and that affects the way it shows us these little absorption lines? We don't know yet. That's a thing we have to work on. I have a gazillion things I have to work on. So there's a lot of important things like this that are waiting while I work on other important things. So if anybody wants to go to graduate school at University of Maryland and come work for me on this, I have possibilities for you. Okay, we're going to wrap up with me talking there. I've gone a little over time, and I have to stop that thing. And it looks like, I may even have lost a few people, but if I haven't completely bewildered you, I would be happy to take questions.
So I just want to say, Dr. Livengood, thank you so much for coming. This was such an interesting talk. I was wondering, your organization's name is an example of, I think, astronomers' phenomenal passion for acronyms. So I was wondering, from an insider perspective, how do you come up with the names for projects such that they fit so well with the acronyms?
Oh, you got to work at it. You got to work at it for a while. We went through, I don't know, probably 7 or 8 different acronyms that I suggested to my colleagues in our lab to see how they felt about it. The truth is, I finally picked SHARP because I liked it, because nobody else was coming up with anything better. We had been asked to come up with because our previous version was, we're the high resolution infrared spectroscopy lab. What more do you need? But we had been told that in order to represent us to the higher ups within Goddard, it was challenging to have to say that every time. And it's more convenient if you're going to say the guys in the SHARP lab. To give you an idea of what else we have, Carrie Anderson has the SPICE laboratory, where SPICE is not particularly descriptive, but of course, science fiction is loaded with references to SPICE because Earth history is loaded with references to exploration because of valuable spices. The best one I've seen, by far the best, is Barbara Cohen has the Moon Girl laboratory. As it happens, everyone in her lab is a woman, but the real reason she chose it is because she is, and she works on the moon. And it's actually doing things like looking at different isotopes in rocks on the moon. They're perfectly happy to look at Mars too. If they can get a Mars rock, then they've done some of that.
Amazing. Thank you so much.
Another project I'm working on right now is an instrument to go to the moon to investigate the amount of water. So first of all, we're working with the Russians who created the LEND instrument that's on LRO, and they were suggesting that they should make a similar instrument, derived from it for Mars, which they were going to call the Mars Exploration Neutron Detector. And we immediately said, no, 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 no. Never name an instrument something like MEND. Bad idea. So they ended up with FRIEND for that one, which is a much better idea. The instrument that I'm working on now to go to the moon to investigate the amount of water is SSOLVE, or SOLVE, the Submillimeter Solar Observation Lunar Volatiles Experiment, SSOLVE. Some of the competition for this kind of thing, there's somebody else that has one where the acronym is WATER, which I think is cheating a little bit because the first word is water in the acronym. But, it really tells you right there what it is that they're going to the moon to do. So we'll see. Let's see. I see calcium carbonate or limestone on Mars. Not as far as I know. I am not a geologist. What they did find in that particular example that I showed you from probing it with other instruments or on the Opportunity rover is that there is sulfate material at the bottom. And one of the things that you can observe on Earth, and one of the many clues, in addition to like the pattern of waviness, is nice to say there was liquid water, but it's actually kind of a weak description. A much stronger description is if you go to something like the Great Salt Lake or the Dead Sea. These are examples of lakes. There's a number of them on the Earth, but these are like the really obvious ones now, where water flows in, but there's no way to flow out. The way that the water leaves is it evaporates. And what happens as water flows over rocks is it dissolves the stuff that the rocks are made out of. Not a lot, but some flows into the lake. And then as the water evaporates away, it gets more and more concentrated with the dissolved material. And if evaporation is outrunning inflow at the time, then it will get to the point where stuff is no longer soluble in the water. And then it begins to precipitate out. And the description, when this discovery was announced publicly, this is all I know about it, was that sulfate minerals dissolve out earlier than, for instance, halite, otherwise known as sodium chloride. And you can actually see a pattern of different kinds of salts, depending on which sulfate, but different kinds of salt material will precipitate out as the water becomes more and more enriched in these dissolved salts as it evaporates away. And the pattern of that deposit that was measured by Curiosity is identical to the patterns you get on Earth when a salt lake dries up. As far as I know, they haven't actually found calcium carbonate yet on Mars. That would be glorious, but it hasn't actually been found. And there is a big question of why is it hard to find carbonate rocks? Just a second, that phone is going to keep ringing if I don't make it shut up. And I have to let the other dog in or he's going to keep whimpering outside the door. Let's see. What is a way to detect water remotely? Excellent question. The way SSOLVE is, it's in a sense remote. What we plan to do is land on the surface of the moon, but then we're going to turn around and stare at the sun. And what we'll be measuring will be the spectrum of what's called submillimeter radiation, which is very high frequency radio, essentially, because this is the same wavelength that is used in your microwave oven. The water in the microwave absorbs the energy that we pump into it at 557 gigahertz. It makes the water hot, and then that heats up the rest of your food. Well, we're going to stare at the sun. We're going to see the absorption from that line at 557 gigahertz. And from measuring that, we will be able to know things like how much water there is. And if the line is very skinny, it will tell us that the water in the atmosphere is cold. And if the line is wide, it will tell us that the water in the atmosphere is relatively warm, because that's a thing we don't actually know that well. And so And the great thing is that because this is a really, really strong transition of water, or a radiative transition, it means we can measure a really tiny amount of water. And that's important because the biggest amount of water anybody suggests at the moon would definitely fit the category of really tiny amount. But there's different levels of really tiny amount. And if there's enough water on the moon, well, then you may be able to do things like, instead of having to go to the North or South Pole, dig it out of the ground, heat up the dirt to get the water out, which is the current plan, you might be able to essentially just put a cup out and collect it when it precipitates out at night, and then warm it up in the morning. The tricky thing being that the amount of water is still very tiny. So that cup has to be like 1 kilometer by 1 kilometer on sides. So it's not trivial, but it's not impossible. And it's probably easier than sending bulldozers to the moon, which is the current plan to eventually be able to mine water on the moon. Let's see, more rovers to Mars in the near future. Absolutely. In particular, the rover on Mars right now is collecting rock samples, and it has no way to send them home. So the plan is that in another, I think, 4 years, the European Space Agency, in collaboration with NASA, will send a rover that will roam around and collect those samples, pick them up off the ground, bring them back to a central point where it will load them into a small but capable enough rocket, which will launch them into Mars orbit. At that point, that rocket will have used up all its capability, and it will have to be captured by another vehicle that will be orbiting Mars and may even be launched another couple of years later to go and collect those samples. And then it will have enough capability to launch itself out of Mars orbit and come back to Earth. In the meantime, the European Space Agency is looking at Mars rovers. I believe Japan is looking at building a Mars rover of its own. And I believe India is looking at doing that. Let's see. Okay, thoughts on proposals to create a new atmosphere on Mars. I am completely torn on the subject. This is one of those things where it's going to take the opinion of a large portion of humanity to figure out what to do on this. We've done a lot of destruction to environments here on Earth. We've killed a huge amount of animals. We've killed whole cultures here on the Earth by being clumsy and just going out and doing, clumsy, disastrous things. To just a second, I have to get my cursor back to where I can see it. But that's where there is life. So the first question is there life on Mars? And if there is, well, do we have any kind of ethical legitimacy to risking the environment of that life on Mars? What if it's only bacteria? Well, is that different? Should we still stay out of the business of bacteria on Mars? What if there's no life on Mars? Well, you've got a pure, pristine environment. Is it legitimate for us to spread our bacteria, because no human can exist anywhere without a cloud of bacteria around us? Chances are, if we send people to Mars, to the surface, we're going to contaminate the surface of Mars with bacteria. Well, what if there is no life on Mars? Does that still make it okay? Or does it not make it okay? And that is above my pay grade. This is the kind of thing where it's going to take thousands, if not millions of people registering opinions to try to understand what we as a civilization should or should not do. Okay. And then as to how you would create a new atmosphere on Mars, I don't know. There's some ideas are crazy, some are not. What is the signal that shows that 018 dip? That is looking at infrared light from Mars. We're actually looking at thermal emission from the surface itself. You and I and everything here, we are busy glowing like mad. Actually, every human being produces as much energy as an old-fashioned incandescent 100-watt light bulb. but it's spread out over a large surface area. If you were to do something horrible and squeeze a person down into the size of a light bulb, bad for the person, but the surface of it would be as hot as an old-fashioned 100-watt light bulb. We produce a lot of heat, and we can measure that. Now, Mars is not nearly as warm as you and I are, but nevertheless, it's warmer than empty space. We can see that infrared light, and we can see the radiative transitions, they're called, of molecules at the different frequencies that they absorb or radiate energy. And that's what we're seeing when we look at Mars. We're seeing that absorption. And because we're seeing it against the warm surface, we're not seeing it in what's called self-emission. That makes it easier in that sense to measure how much of it there is. Nevertheless, there's also quirks of the temperature of the rest of the atmosphere affect how much of that absorption is available for us to see. So on Venus, that's why I'm not able to just, slam my hand down and say, by Godfrey, Venus is poor in oxygen 18 carbon dioxide. And it's why I can't look at my spectra of Mars and say, by golly, the cold hemisphere, the winter hemisphere, is poor in oxygen 18 CO2. That means I'm right. We can't be sure of that yet, because a quirk of Mars is that if you filled up the ocean basins on Mars, what we believe were once ocean basins, with water, what you would see is that the whole northern hemisphere of Mars is pretty much ocean, and the whole southern hemisphere of Mars is pretty much continent. And that means it's higher up. And because of that being higher up, the line of atmosphere through which I'm looking, the actual path, is shorter looking at the southern hemisphere than looking at the northern hemisphere. And it's possible that that is accounting for the difference we're seeing. We have the software we need to analyze and model the spectra. But as it happens, we've gone through a couple of system upgrades on my computer since the last time we installed that software, and it doesn't work on my computer now. And we can't get together very easily for my colleague to help hold my hand through the process of installing it. So right now, we don't have the ability to model it very well. We have to get back to that. Did I like the Martian movie? I thought it was great, except, of course, for the first thing, as everybody says. The first thing, the wind just doesn't blow that hard on Mars. It blows that fast, but it doesn't carry that much momentum. I was kind of willing to give it to him. Plus, the way that Andy Weir wrote the book was he actually accepted critique from people while he was writing on his blog, and he would go back and edit the chapters and make them more consistent with real science and engineering, which is part of why the book is so solid on its science and engineering for the most part, because he accepted critiques and modified the book in the process. But his big opening MacGuffin, he was kind of stuck with that and he left it. The one other thing is, in reality, hydrazine will really kill you dead. So dripping hydrazine inside the habitat without his spacesuit on at the time would be an extremely bad idea. Let's see. What is the main reason for going for Mars before reaching the moon and building a base? There's back and forth on that. There's a whole community of lunatics, as they genuinely call themselves, that say moon first, Mars later. And that's actually more or less the plan right now, not to build a moon base as a way of building vehicles there to go to Mars, but to build a moon base to practice with the processes of building a complex structure that people can live in for a long time. I kind of like that theory. The thinking with the Augustine Commission, which is, now 13 years ago, was that although going back to the moon or going to Mars sounded awesome, Congress did not appear to be willing to put up enough money, because one of the challenges is that landing on the moon takes a special kind of vehicle, because there's no atmosphere, you can't parachute, no heat shields, you got to use rocket engines. Landing on Mars, there is an atmosphere, you need a heat shield, but it's not enough atmosphere to slow you down if you have something as big as a human occupied spacecraft, which means you still need rockets. So what you end up with is that the engineering problems that you need to solve to land on the moon will not help you with solving the engineering problems to land on Mars. And both of them are very expensive. Whereas another option was to try to fly to an asteroid where you don't have to land, but you have to stay in space for several years. And so at that point, we were going to try that. And at this point, you'll notice we seem to be largely planning on going back to the moon. And I think we're going to do that. Let's see here. How does seasonal variation isotope ratios provide insights in Mars geology and atmospheric entry? Or is it simply a factor that necessitates corrections in the data? Well, it is a correction in the data, but the big thing is we don't know how enriched the atmosphere of Mars really truly is now. My measurements seem to suggest that it can be more enriched than what we get from the Curiosity rover. That's consistent with losing more atmosphere, which means that Mars would have started with more atmosphere, which tells us something about the history of planets like Mars and Earth and Venus. How much do they get born with? So that we can then say, how quickly do they change? Because we want to look at planets orbiting other stars and have an idea, where is it in its history? What is likely to be happening there? Even if we can't see the details, maybe we can measure its spectrum. What's going on? And we need the planets in our solar system as a guide for that. One of the big questions is how much of this stuff is frozen into the ice caps? If you were to thaw those out into gas, would that change the answer? And so right now we're just trying to find out, am I just right at all? Or have I fundamentally misunderstood the data? Because that's always a possibility. Does it matter? Because if it matters, it means that we need to make our measurements differently, which means we need to understand the atmosphere of Mars differently, which means we have a better handle on how much atmosphere Mars once had. With respect to Venus, then, Venus has no meaningful seasonal behavior as far as we can tell, but Venus actually is in a more elliptical orbit than the Earth is, for instance. So for Venus, you actually do get some change in seasons depending on how far it is from the sun. And there are things that change in the upper atmosphere. Okay, so we've got some explanations there. So maybe I was answering the question that wasn't being asked, but what the heck, it was still fun. What up?
It looks like there aren't any more questions in the chat right now. So if we don't mind just taking a quick break from the questions, I was actually hoping we could take a picture with our guest. If everyone wouldn't mind turning on their video briefly, so I could just take a screenshot of all of us together with our guest speaker. That would be great.
Here, I'll zoom in manually so that my nose will look giant.
All right, let me just give everyone a minute to get their cameras turned on, and then I will actually have to take 2 screenshots because there's enough people that there are like 2 Zoom screens. So I'll let you know when I'm taking the first screenshot and then when I'm taking the second screenshot. Okay, I'm going to take the first screenshot in just a second, so everyone smile. Okay, perfect. And then just give me 1 second to save that one. Okay.
While we're waiting, could I ask, Rich Bova, are you by any chance related to the famous Ben Bova or not?
No, I'm afraid not.
Alas.
I've asked that question many times.
I'm,
no.
I'm sure.
I wish I was.
Okay. And then if everyone could just smile again, I will get one more screenshot of the second page. Okay, I think we are good.
Yeah, I can tell you there are not that many famous Livengoods. We're pretty obscure. There is Scott Livengood, former CEO of Krispy Kreme, was famous after his embezzlement trial and imprisonment. And there's a Livengood out there somewhere who is a football coach. But for the most part, we're pretty obscure. The weird thing, though, is there is another Timothy H. Livengood who is also a contractor at a NASA center. So every now and then when one of us gets involved with somebody new at work or joins a new research group, we will get the other guy's mail for a while because somebody will have typed in Livengood and selected the first thing they saw. And, I get his, he gets mine. So we've known of each other's existence for about 25 years or so. Let's see. Yeah, back to the Venus question. I see it also included talking about sending missions to Venus. The Venus community feels very hard done by within the NASA family because we haven't had many Venus missions. And NASA has had no Venus mission since Magellan, which is about 30 years ago now. I've seen that there is another radar mission in preparation for Venus, which I'm sure still irritates a bunch of the Venusians because they would like to do other stuff. There are plans for long duration landers for Venus. There's a mission in proposal that is hoping to be selected called Da Vinci Plus, which will be a short duration lander. Their plan is to land, function for 2 hours on the surface of Venus, and make geochemical measurements of the rock, the atmosphere, and so on. Of course, if they live longer than 2 hours, that would be great, but that's not a big part of the mission. And then they have plans, though, to try to create landers that would be able to have a functioning refrigerator that would be able to keep it at a temperature where the electronics would not all fail for weeks or months. And that's not easy because how you make a refrigerator that works when it's been planted in melted lead, essentially, because that's the temperature of the atmosphere, that ain't easy. I believe they're talking about using the working fluid in the refrigerator, maybe paraffin or some other wax type substance. It's a hard problem. Personally, what I want is to send a Zeppelin to Venus so that we can fly along at modest altitude and see the ground. And the cute idea I came up with is that if you inflate a balloon with water on Venus, then if you drop too low in the atmosphere, it heats up and it takes you back up higher. But if you go too high, the water will begin to condense and deflate the bags a little bit, and you'll drop down low, which means that it has a built-in altitude stabilizer, even if the electronics fail at some point, so that you will never drop too low or go too high. But it does mean you have to build electronics that will work at the boiling point of water, which we can do. The tricky thing is that on Venus, that means I believe that's at about 40 kilometers altitude. So you've still got plenty of atmosphere and plenty of haze below you at that altitude, interfering with your ability to see the ground. But that's why Venus is the only one of the major rocky planets where we don't have any kind of remote, visible light reconnaissance of the surface, which makes it hard to get a measurement of what the rocks are made out of. All we have is radar, And radar guys will tell you the reason why two different rocks look different. But when you ask them, and so what mineral does that tell me it's there? It's all I know is it's different. So, having landers on Venus would be awesome, but hard, very, very hard. Let's see. What will the next generation Mars helicopters be capable of doing? Don't know. I mean, right now, that little thing, they could use it to scout ahead, which would allow the rover to drive faster. The big thing that keeps the rovers slow, though, is that they want to visit all the nifty rocks along the way. So, driving faster isn't really an issue there. Certainly, they'll have better cameras. We've become better and better over time at building cameras that have great resolution in very lightweight packages. But presumably, at some point, they'll want to do things like be able to fly an instrument to a rock that you otherwise could not get a rover to tell you something about what it's made out of, things like that. Let's see, there's a question, have you met before? Well, I'm not sure who they mean, have I met? As far as I know, I haven't met anybody here. If I've met the other Tim Livengood, only by email. And by Facebook. We are, of course, Facebook friends. Given that the name Timothy Livengood is kind of rare, I did at one point make Facebook friends with all the other Timothy Livengoods that were on Facebook at the time. But since it turns out a lot of us are, let's say, anti-science, we're not friends anymore. They dropped me. They weren't interested in what I had to say. The last lander on Venus. No. It landed like almost 2 hours it lasted, which is still the max they got out of it. I've seen, let's see, well, a few different people have published the picture of every picture ever taken from the surface of Venus. And it's like 12. Because not only is it hard to get a working camera to the surface of Venus, but it is also hard to transmit the data back because, like, you can't put a great big dish antenna there because the electronics that are part of the antenna get overheated and stop working. So it's hard, even though the wind blows very slowly. I believe I have used up every question that was in the chat. So throw in some more if you want, but otherwise it sounds like we're getting close to quitting time. I've got a big pot of chili waiting for me in the other room and some, good TV tonight. We're watching quality TV tonight. Thank you.
All right, yeah, well, if we don't have any other last minute questions, thank you very much, Dr. Livengood. This was a really fun talk. I think it's probably one of the first times in a while that the Astronomy Club has had a guest speaker from outside the university. And I think this was a really cool and exciting event. So thank you so much for doing it.
Well, I work on other stuff too. So if you have another planet you're interested in sometime, I may have looked at it.
Definitely. We'll keep that in mind for the future. Thank you so much. Okay.
Thank you, everyone. Good night.
Thanks. Good night. And to everyone who is on campus and was possibly interested in the last part of AstroFest tonight, which would have been observing on the roof of ESS, unfortunately, it is cloudy tonight, so we will not be doing that. We may reschedule to a different date sometime next week if there are any clear nights. So if you're not already on our mailing list or in our Discord server, just let us know and we can send you the link to join one of those. But thanks everyone for coming tonight.